Welcome to the first video for Chapter 4. Chapter 4 is the first chapter in Module 2 of our course, where we bridge the gap between the material from Module 1, where we did simple descriptive statistics, and the material that we will cover in Module 3, where we cover inferential statistics. In this first chapter, we're going to cover a number of key concepts, including defining experiments and counting rules, basic relationships in probability theory, Bayes' theorem, which is a special theorem in probability theory for updating probabilities based on new information, and experimental outcomes and their probability. So in this first chapter, what we want to do is define what we mean by a statistical experiment. Then we will want to enumerate all of the possible outcomes of an experiment, or at least be able to count the number of possible outcomes in an experiment. This is a key step to being able to calculate the probability that's associated with the various outcomes of an experiment. In other words, attaching probabilities to what we will call the sample space. Ultimately, what we will do in later chapters is define random variables over that sample space, and we will be able to talk about the probability distributions of various types of random variables. Here are some basic definitions. First, an experiment is any process that generates well-defined outcomes. And one thing that I mean by well-defined is that the outcomes of the experiment are mutually exclusive in the sense that they will be defined such that when one outcome of the experiment occurs, the other outcomes of the experiment do not occur. The sample space, then, is the set of all the possible outcomes of the experiment. An experimental outcome is also called a sample point within the sample space. It is over this sample space that we will define or attach probabilities to the outcomes, and then ultimately define random variables. Here are some examples of experiments. Start with something very simple, like tossing a coin. The simple toss of a coin can be seen as an experimental outcome. There are two mutually exclusive outcomes that are possible when you flip a coin. You can either flip heads or you can flip tails. I should also mention that with an experiment, which outcome occurs is a matter of chance. Typically, we think of a 50% chance of flipping a heads and a 50% chance of getting a tails. The idea of an experiment can also be extended to situations that are important in business. For example, you can imagine working for a quality control department within a company, and you're inspecting parts. So you might take a random sample of parts. Sometimes inspecting parts at a company involves actually destroying the part. So you may not be able to fully look at every single piece and inspect it before you ship it off to a customer. In this sample, there are two outcomes. Either a test is passed and the part is found to be non-defective, or the part does not pass the test and it's found to be defective. We can also think about, for example, conducting a sales call. That would be another business application. The results of the sales call could either lead to a purchase or no purchase of the output that is being sold, or the product that is being sold. To come back to parlor type games, we could think about rolling dice. If we roll one die, there are 6 possible outcomes. They're mutually exclusive and well defined, and which outcome we receive is a matter of chance. We can roll either a 1, a 2, 3, 4, 5, or of course a 6. Also, we could think about playing a football game. There are 3 mutually exclusive possible outcomes that are largely, or at least to some degree, a matter of chance. Our team could win the game, they could lose the game, or the game could be tied. These are all examples of experiments. Here's the multi-step experiment counting rule. We're going to cover 3 rules here. And this is the first. It's the simplest and it's the easiest to understand. Our next counting rule will actually be seen as a special case of this rule. If we have an experiment that consists of a sequence of k steps in which there are n1 possible results from the first step, n2 possible results from the second step, etc., then we can find the total number of experimental outcomes by taking the product of all the different possible results within each step. Now, in order to motivate this, let me give you a very simple example. Let's suppose that we toss a coin 2 times. If we toss a coin 2 times, it's clear that there are 4 possible outcomes. This is intuitive to all of us. We can either flip a heads and then a heads and then a tails and then a heads, or we can flip 2 tails. So there are 4 possibilities. On each flip of the coin, there are only 2 things that can happen, either a heads or a tails. So it won't be surprising to you to find out that the number of possible outcomes in an experiment of flipping a coin twice is 2, because there are 2 possible outcomes in the first step. Then we flip the coin again, and there are 2 possibilities in the second step, and 2 by 2 times 2 is equal to 4, the total number of possible outcomes in the experiment when we flip the coin twice. Now, when we flip a coin twice, it's very easy to count up the number of possible outcomes and enumerate the sample space. But now, imagine you're going to roll dice, maybe not even twice, but just once. Now, when we roll, we can get a 1, a 2, a 3, a 4, a 5, or a 6, as we saw in the previous slide. It's very easy to enumerate and count up the number of possible outcomes. But now suppose we take that die and we roll it 2 times, twice in a row. Now the possible outcomes expands considerably. In that case, we can roll a 1 and then a 1, a 1 and then a 2, a 1 and then a 3, etc., out to a 1 and a 6. But we could also roll a 2 and a 1, a 2 and a 2, a 2 and a 3, etc., right, all the way out to a 2 and a 6, and we keep going all the way out until we roll a 6 and a 1, all the way through a 6 and a 6. It's very cumbersome to list out all of those possibilities and count them up, and that's a fairly simple experiment, just rolling a die twice. So we need these counting rules in order to be able to find shortcuts to figuring out the number of possible outcomes in more complicated experiments. So in the case of the dice, if we roll twice, the number of possible outcomes is very easy to find, since in each step there are 6 possible outcomes, and 6 times 6, since we're rolling twice, is equal to 36. We know that there are 36 possible outcomes. So these combinatoric counting rules are very, very helpful for understanding probability theory. Sometimes we can also represent a multi-step experiment if we want to enumerate all the possible outcomes in a tree diagram. This can be very informative, and it's a good pedagogical tool, and I will use it a few times throughout this module. Again, coming back to our example of tossing a coin 2 times and recording the result for each toss, we said there are 2 times 2 equals 4 possible outcomes. And note again that that's an application of the multi-step counting rule that we just covered. And like I said, we could roll 2 dice and we can record the result. And there will be 6 times 6 equals 36 possible outcomes. Here's a more complicated example. Suppose we draw a 5-card poker hand from a standard deck of 52 cards. The question is, how many different ways are there to draw 5 cards? The answer, according to our multi-step counting rule, is that we can draw the first card in 52 ways, because there are 52 cards. Now, we're not going to replace the card after we have drawn it, so when we draw the second card, there will be 51 ways to draw it, etc., all the way down to the 5th card, and there will be 48 ways to draw the 5th card. Taking the product of all these terms implies that there are 311,875,200 different possible ways of drawing a 5-card poker hand. You would never want to sit down and enumerate all the different possible ways of drawing a 5-card poker hand. You would probably be sitting at your computer for, for weeks. Here's our second counting rule, a counting rule for permutations. First, before we get into this slide, anytime you see the word permutation, I want you to remember that the order of the objects matters. So permutations imply that the order of objects matter. In other words, we can have the same object in a set, but if we list them in a different order, then it's considered a different permutation. You'll see this in some examples that follow. The number of permutations, then, of n objects taken n at a time basically means that what we're going to do is we're going to take a set of n objects where n is a number that's larger than lowercase n, and we're going to take n of them at the time, and we're going to count up the number of ways that we can get n at a time where the order matters. So, I'll give you some examples of this, but one of the examples that we will look at is the poker hands again. So you can imagine that we have 52 cards in a deck. Like I said before, we've got those cards in the deck, and we're taking 5 of them at a time, as we did in the previous example. And in the previous example, implicitly the order mattered. So if we drew, say, an ace of spades and a 3 of hearts in one hand, and then in another hand that had all the same 5 cards, but we drew them in a different order so that the 3 of hearts came before the ace of spades, that would be considered a different experimental outcome. Okay. So this is a very useful counting rule, as it provides a mathematical shortcut, and it's really a special case of the multi-step counting rule that we saw previously. So here's the formula, which is not really as scary as it looks. This notation means permutations, that's P, of n objects, the number of cards in a full deck of cards, in the example we've been talking about, taken lowercase n at a time. For a poker hand, standard poker hand, lowercase n would be equal to 5. Okay. And this is n factorial. We'll talk more about that in just a second. And this notation here is notation that you shouldn't really know yet, but we're going to cover it in another slide in just a minute. But it means combinations of n taken n at a time. Don't worry about that right now. We'll come full circle that on that in a graph or two here. But the formula for calculating the permutations is to take capital N factorial, the number of cards, for example, and factorial means that we take n and we multiply it by n minus 1 times n minus 2, etc., all the way down till we get to 2 times 1. You should be familiar with factorial notation, and if you're not, I highly recommend that you look it up on Wikipedia or look it up in a math book. Lowercase n factorial is, of course, lowercase n times lowercase n minus 1, etc., down to 1. And I would just remind you that 0 factorial is always equal to 1. Here's an application. Talk about an application. I'm going to do a very simple application here. I'm going to pick 2 names from 3. These are the names of my children, Sam, Sophie, and Josie. I want to know what are the number of different permutations of size 2 that I can create from these 3 names. Again, in this case, it's very easy to enumerate, but it's quite illustrative for using the counting rule for permutations. According to the counting rule for permutations, I would take the total number of objects that are in my set, that is 3 names, Sam, Sophie, and Josie, and that would go in the numerator, 3 factorial. Then in the denominator, I will put capital N factorial minus lowercase n factorial. That is 3 factorial, and I'm choosing 2 names, lowercase n is equal to 2, at a time. So 3 minus 2 factorial. So that is 3 times 2 times 1 divided by 3 minus 2, which is 1 factorial, which is just equal to 1. So the answer here is clearly equal to 6. I should be able to create 6 different permutations of size 2 from this set of 3 names. And here they are. I can pick Sam and Sophie, Sam and Josie, Sophie and then Sam, Sophie first and then Josie, Josie and then Sam, or Josie and then Sophie. I would point out two things about this list. First of all, Sam and Sophie appears, but also Sophie and Sam appears. Sam and Josie appears, but also Josie and Sam appears. So clearly, in this case, the order in which I draw the names matters, and Sam and Josie is seen as being a distinct result, or a result that is distinct from Josie and then Sam. The other thing that I would point out is that you don't see, for example, Sophie and Sophie, or Sam and Sam, or Josie and Josie. And that's because we are sampling without replacement. Once we've picked one of the names from the three, we don't return it to the list to be selected potentially again the second time. Here's the counting rule for combinations. The number of combinations is similar to the number of permutations. But the number of combinations is going to always be smaller than the number of permutations. And the reason for this is that when we talk about combinations, the order in which the outcome of the experiment, the elements in the outcome of the experiment, the order in which they appear doesn't matter. Okay, so combinations will be very closely related to the number of permutations, but will always be a lower number. So, for example, here's the formula. Here's the formula for combinations. This actually appeared. This notation, I guess, in the middle here actually appeared in our formula for permutations. So, like I said, this would come all full circle in a slide or two. The number of combinations here really looks a lot like the formula for the number of permutations. In fact, if I circle these terms, those are that is basically the formula for permutations. But I'm reducing the number of permutations by dividing the result by n factorial. This is very intuitive, as we'll see in a moment when we come back to looking at the list of three names. So in combinations, we're doing something similar to what we did with permutations, but in this case, the order in which the elements in the experimental result, the order in which they occur, is actually not consequential. So again, we'll come back here to the 5-card poker hand. If you think about what we calculated before with the 311 some odd million different possible ways of drawing 5 poker hands, that wasn't really that useful for thinking about the way that we play poker or assign probabilities to different poker hands. A poker hand that's superior to some other poker hand is superior because it has a lower probability of occurring. But we don't care what order we draw the 5 cards in. If we're going to draw a royal flush, we don't care whether or not we drew the ace in the royal flush first or we drew it last. It doesn't matter. What matters is the combination of the cards, not the order in which we drew them. So the rule for combinations would be more useful in thinking about the probability of poker hands. So how many poker hands then are there? Well, there are going to be fewer than 311 million, that's for sure. Here's the answer. We take our 52 cards, so we have 52 factorial in the numerator, just applying the formula from the previous slide. And we have 52 minus 5 factorial. That showed up when we calculated the number of permutations too. But in this case, we've also divided the result by 5 factorial. So in fact, the number of poker hands that are actually possible is quite a bit smaller than the number of permutations. There are 2,598,960 different possible poker hands.